mechanical switch. Thyresistor also pass turn on and off. Thyresistor is simple devices. First, I'm gonna explain what it is here on the figure. IT on state voltage drop BTM. On state characteristic forward conduction. Latching current IG 3 IL 2 IG2 papunta IG2. Papunta naman sa IG1 going to IG0. Holding current IHBT reverse breakdown. Voltage forward blocking state characteristic IDRM at BDRM of state characteristic for the reverse blocking forward breakdown voltage. So in this, SRC acts very much like a switch. When it's turned on, acts like a closed switch. When it's turned off, it acts like an open switch because it's solid state devices. The switching action is very fast. Electrical characteristics of SRC are shown in the figure below. Next slide. Requirements to turn on Thyresistor SCR's breakdown. Ano nga ba to? Voltage should never be exceeded because the SRC goes into conduction even when a gate current is not applied. It remains turned on even if the breakdown voltage is reduced. 1. The Thyresistor must be forward biased. There must be sufficient trigger current into the gate through the gate cathode junction. Requirements to turn off a Thyresistor. The main terminal IT current must be below the holding current IH. The Thyresistor is reverse bias. So next slide. In figure 5.3, ideal waveforms of SCR main terminal voltage and load voltage. First, her firing delay angle of about 60, conduction angle of 120. For a firing delay angle of 135, conduction angle must be of 45. Firing angle delay is defined as the number of degrees that the SCR is off before it's turned on, whereas the conduction angle is number of degrees that the SCR is on. Next slide. Typical gate triggering circuit. First, resistive circuit. Supply is a AC, sinusoidal. In figure 5.6, dito sa figure natin, versing for triggering circuit for an SCR. When switch is open, the SCR can never turn on. The load therefore is de-energized. When switch is closed, there will be a current into the gate G of the SCR. So next slide, 7. The variable resistance R2 will control the firing delay angle. If R2 is low, IG will be sufficient to fire the SCR when the supply voltage is low. Early firing or delay angle is small, and vice versa. R1 is to maintain a fixed value of gate resistance when R2 is set to 0. Once the SCR is fired, all the load current will pass through it since it is closed switch and there will be no gate current. Waveform of the load voltage will be similar to that figure 5.3, yung kanina figure na pinakita ko sa inyo. So next. Disadvantages of circuit, it's that the maximum firing delay angle is 90 degrees only. The fact is shown in the figure 5.7. If the supply voltage is DC, the SRC will remain on until the supply is removed. On one of the application of the simple circuit is an alarm system, whether that's a fire alarm or anything. In figure 5.17, ideal waveforms of SRC main terminal voltage and gate current. The dash line, yung makita ang dash line, represent the gate current necessary for the fire SCR or IGT. Gate current is low, resulting in a firing delay angle about 90. Gate current is trigger, resulting to a firing delay angle of nearly 0. Next slide. Capacitor triggering circuit. Dito naman, in figure 5.8, SCR gate control circuit, which is important. Improvement of the circuit 5.6, yung kanina. Dito, the capacitor will provide a greater range of adjustment on the firing delay angle. Dito sa figure natin, an improvement of the circuit where a capacitor is added at the bottom gate lead resistance. The capacitor will guarantee the possibility of firing delay angle to be beyond 90 degrees for the negative half cycle of the supply. The capacitor will charge in the reverse direction, top plate negative and the bottom plate positive. Next slide. For positive half cycle, the capacitor takes time to fully discharge and then charge in positive direction. Top plate positive and the bottom plate negative. This will delay the current from flowing to the gate until the capacitor is charged higher than positive 0.6 volts. The delay will depend on the value of resistor 2. The bigger the value of resistor 2, the slower the charging and the bigger the firing delay angle. So alam naman natin yung resistor, siya yung magde-delay. Ibig sabihin, mas mataas daw na resistor is mas mabagal daw magcha-charge. And yung capacitor naman, usually ay naman talaga ginagawa niya is magcha-charge muna siya bago pumasok doon sa Thyresistor natin. So dito naman, next slide tayo. Figure 5.9 shows a triggering circuit similar in the operation to the previous one. Yung kanina yung sa capacitor. The insertion of resistor 3 requires the capacitor to charge higher than 0.6 to trigger the SCR. So the triggering is further delayed. The firing is further delayed by the insertion of capacitor 2 or yung C2 instead of immediately fire the SCR. Once the BC1 is enough to overcome the resistor 3 drop, it will be used to charge capacitor 2 and only after capacitor 2 is charged higher than 0.6 volts. The IG will flow into the gate. Control circuits, either one of these circuits provides a greater range of adjustment of the firing delay angle than the circuit of figure 5.8. For given capacitor values, usually 0.01 to 1 microfarad, the minimum firing delay angle is set by fixed resistor R1 and R3, and maximum delay angle is set by the size of the variable resistor 2. Practically, R1 plus R2 times the capacitor 1 and resistor 3 times the capacitor 2 should fall in the range of 1 to 30 milliseconds for a 60 Hz supply. Two problems are associated with the previous triggering circuit: temperature dependency, inconsistent firing behavior between SRC of the same time.